On behalf of the organizing committee, I welcome you again to the American University of Sharjah and to the United Arab Emirates. We have a rich technical program over the next couple of days. We have 2 keynote speeches by two leading researchers in their fields, 2 tutorials, and 12 technical sessions. We've received submission from 25 countries from North America, Europe, Africa, and Asia. About 128 papers were peer-reviewed, and 77 papers were accepted. That's an acceptance rate of 60%. Without any further ado, let me now invite AUS Chancellor Peter Heath for his opening remarks. Peter.
Thank you very much. It's a great pleasure to welcome you to this university. For those who haven't been here before, I hope you take advantage of the opportunity to not only enjoy the sessions and your colleagues, but also to wander around, get some of the students to show you around both the facilities that we have in the engineering school. I can't call it a school, the College of Engineering, my apologies, Mr. Dean, as well as things like the Student Center and other activities that we have. I'm welcoming you here today on behalf of also our founder and president, His Highness Sheikh Dr. Sultan bin Mohammad Al-Qassimi. He's a member of the UAE Supreme Council and the ruler of Sharjah. And let's see. There he is. Who has, really been an inspiration for this institution from the moment that it was conceived, and it was his conception. I know that many of you have traveled a great distance to be here today, as far afield as the US and Canada, as well as Japan and many cities in between. Let me tell you a little bit about the university, if I can just have a few minutes of your time. His Highness Sheikh Sultan established this institution in 1997, and his vision was that it should become the leading institution in higher education in the region, known for great undergraduate education and working very hard to develop our graduate profile and our teaching and research on the advanced level. He also mandated that AUS cooperate with the cultural, economic, and scientific and industrial centers of the UAE and the region. We are intended to be an active participant, not only in education, but also in developing the social and economic progress of the region. 15 years later, we have been named one of the top 500 universities by the QS ranking system. And nobody likes ranking systems until you're ranked in them, then we really love them. So we hope to be the number 400 and 300 as time goes by. And really our mission is to provide the best possible education for our undergraduate students and our graduate students, and the best possible environment for our faculty to pursue their careers. And I think despite some frustration we've heard, that I hear continually from faculty, why we're not doing more, I think that the faculty have done a wonderful job in dedicating themselves to their undergraduate and graduate education. And the university has done a remarkable job in coming as far as it has in the short time that we've been in existence. Now, I have a page and a half of how great our IT systems are within the university. But I just want to summarize it because I don't want to take more of your time. It's clear from even what our IT people, and these are not our professors, are saying, is that we continue to be in a time of remarkable change. And this change is having an impact not only on the technical level, but really also on the social and economic and even more sort of civilization level of how one conceives of communication, how one conceives of the use of technology. And despite the fact that we lost our email for 6 hours yesterday, and our poor IT people had to spend hours and hours trying to repair it, this transformation in communications and in IT is having continued and daily impacts on our lives. We aim at AUS to deliver the best possible facilities in terms of communications and IT, and we rely on the innovations that you as faculty members and engineers and investigators and research in this field pursue in order to that we as an institution can take advantage of what you are doing. So this is really a very welcome conference. We're delighted that you're here. We'll probably understand, at least I will understand what you are proposing or talking about in terms of innovation, probably in about 4 years. But it's extremely important what you're doing, and it's a great opportunity for our students to listen to these sessions and for you to bring your knowledge to us as well as for our faculty to participate actively in these sessions. So welcome once again, enjoy your time here, and thank you very much for coming.
Thank you, Chancellor. Thank you, Chancellor. Without any further delay, let me start with the first keynote speech by Professor Munir Hamdi, Head and Chair Professor of the Department of Computer Science and Engineering at Hong Kong, the University of Science and Technology. Professor Hamdi is an IEEE Fellow. He has served on the editorial board of various prestigious journals and magazines, including the IEEE Transactions on Communications, IEEE Communication Magazine, Computer Networks, Wireless Communication, and Mobile Computing, just to name a few. His speech today is titled Next Generation Massive Data Centers for Cloud Computing Applications. Thank you, Munir. Your presentation is already here.
So, good morning, everybody. Before I start, I want to take this opportunity to really thank the organizing committee, and in particular Dr. Ali, Dr. Taha, and Dr. Isam for inviting me to this conference. And I want also to thank the university, the American University of Sharjah, for hosting this. So I came all the way from Hong Kong, and I've been to this campus before. It's a very nice university, and indeed it is making a name for itself in many places. So I will go right directly to the talk. I'll be talking about next generation data centers for scalable cloud computing applications. Nowadays, many people talk about cloud computing, so hopefully I will give you a bit of flavor about the type of research that it is being done in this area. So basically, I will try to motivate the trends in cloud computing and data centers in general, because obviously cloud computing is built on top of data centers. Also, we'll try to look at the data center requirements, the cloud application requirements, and we'll go briefly into some of the research areas that my team and some of my colleagues are doing in this area. Then I will try to pinpoint to some future directions that I feel that are very important. Then I'll conclude. So basically, I mean, in general, I mean, IT is becoming part of our life. But nevertheless, there is what people call the crisis of IT. It's basically every organization, every company is under a tremendous pressure to accomplish more with less resources. Whether, when you talk about resources, whether it is infrastructure, whether it is finances, or whether it is human capital. And on the other hand, I mean, today's companies and organizations, they are relying more and more on IT. So basically, as the Chancellor just mentioned, I mean, living without email for a few hours can be a huge problem. So essentially, I mean, we cannot survive without IT. On the other hand, besides universities and organizations, we have a huge proliferation of the internet, and nowadays, especially with with big companies like Google, Microsoft, Facebook, and so forth, they have been stressed out because they are providing services not to millions, but now even to billions of users. So essentially, all these, they have requirements, stringent requirements, and these requirements, they can only get bigger and much more important in the future, because they are becoming an essential part of our business, our education, and our social needs. So basically, if we look at IT within the business environment, essentially about 70% are captive in operations and maintenance, meaning the work that IT people do are related to operations and maintenance. And I was talking last week to the head of the IT section of HSBC Hong Kong, where they have about 3,000 IT working for their operations. I mean, they are dealing with these type of problems. They are complex, inefficient. They do over-provisioning. Whenever you have a problem that you cannot solve, the easiest solution is to do over-provisioning. But of course, you have to pay for that. And low productivity and so forth. Also, the business innovation is throttled to about 30% of its own potential. So there is long delay to business value. There is an unpredictable service levels. And the business is not agile enough because of many constraints. I'll give just very few examples. So for example, the data growth in terms of storage capacity. I mean, storage capacity, even at the university level, it is growing at a very high rate. So on average, it's about 72%. And for this, even though the cost of this storage is going down, but because of the value of the data that it holds, that we need, it is increasing. So there is an increasing cost in terms of the management. So there is a gap between the cost of storage and the management of these storage. So in general, probably, I mean, we try to look at storage costs as it is growing in terms of size and cost, but the killer is the management of this type of storage. So in fact, for $3 equipment, you will pay about $7 for its management. Another example, for example, personal genome data. I mean, now it is. I was just reading last week Time magazine. In fact, the cover of Time magazine was talking about something like this: is that it is becoming very important. One, for scientific curiosity, is how our and other species, for example, genomes look alike, how genomes differ by species, how genomes differ by individuals, and so forth. But also there is very, very important practical use. And this is what, for example, Time magazine was trying to focus on, is in terms of personal identification. So it is like our true finger identification. And this personal identification, because it is unique for everybody, then it can be used, for example, for personalized medicine. And there is a huge trend towards personalized medicine for effective treatment. And to be able to do this, nowadays, obviously, it is very time-consuming in terms of computation, and also it needs a lot of storage. So meaning that it cannot be done easily. But the goal is basically, at a certain point in the near future, we will have our own personal identification in terms of genome data in the USB in our pocket. So we can give it to a pharmacist to give us the proper medicine and so forth. So that's why, for example, these data centers, they can be a powerful tool to solve, to achieve this goal. So here, even though the cost is going down and the amount of databases and the amount of genome bank information that we are accumulating is extremely large, but sometimes it does not make sense for individuals to have a supercomputer to be able to have their own genome data. So again, this is also a very nice application for data centers and cloud computing in general. So basically, what's the goal of cloud computing? From a user's perspective, is that you want to have the illusion of infinite resources available on demand. So basically, you have no upfront commitment, whether you are talking about storage, whether you are talking about computing power, or whether you are talking about applications that you need to use, or software, and so forth. So ultimately, it becomes a commodity like electricity. So this is the ultimate goal. From a provider's perspective, is basically you dream of cheap and large-scale IT resources with, of course, easy maintenance and management. And for this goal to happen, of course, we need to have a huge data centers. So basically, these data centers, they are the key infrastructure enablers for this type of computing or IT trend. Now, in terms of the goal of cloud computing, which sits on top of these data centers, is that the IT resources and services, they should be abstracted. So in our case, we don't care how many servers, what's the speed of your network, and so forth. And basically, this abstraction should be provided on demand, and of course, it should scale to millions and millions of users. So basically, this cloud is that common, meaning it's for multi-tenancy, it's not for a single user. Location independent, meaning that I can access it anywhere. Online, the connection can be online, and everything is virtualized. Utility, pay for use. And on demand, meaning that you have an infinite, immediate, and invisible scalability. And there are many types of cloud services out there that are built already and they are being used. So for example, if you want to just use the infrastructure, then they call it infrastructure as a service. Or you want to use the platform. For example, Microsoft Azure platform. It's a platform that allows you to write your own applications. Or it can be even software as a service. And all these types of cloud services, they are available nowadays with Amazon, with Microsoft, and so forth. So for example, if it is infrastructure as a service, then basically the user needs to manage this, and then the service provider will manage this. And if it is a platform as a service, the user will manage this, then the rest will be managed by the other side. And if it is software as a service, then it is totally managed by the cloud computing vendor. And the cloud services and applications out there, they are too many. And you can, and they are growing. So it is there to stay. And it is developed by giants like Google, Microsoft, Amazon, and so forth. So basically, as I said, the data center is essentially the key enabler for this cloud computing trend. And so the idea here is essentially you want to keep all the servers and hardware in one physical location. And in that case, you will be able to reap much more benefit, and you provide much easier in terms of maintenance, because if things are very distributed, then it can be quite difficult to maintain. And also, at the same time, again, you try to offer high availability, because if you don't solve, for example, I want to access my email or certain application and I don't find it, then it is a problem. Then in that case, basically, you will not have any customers. So basically, you need to have a high availability and business continuity. And also, it needs to accommodate all the changes as the business change and grows. So to be a viable a cloud computing vendor, you need to cater for the growth and for the changing nature of your clients. And here, I mean, that's why, in some sense, it is becoming a very hot business model and a very hot IT area. So here, just a few examples, because typically the sizes and the nature of these data centers, they try to keep them confidential. But some of them, you find some information in the internet. So for example, the Microsoft data center in Washington, it is as big as 10 football fields. So it is huge. And this is some of the things, for example, about 1,000 kilometers of electrical wires and so forth. Yahoo, it's smaller, obviously. This is Google in just this place. But if you look at Google worldwide, nowadays, they have much more than 1 million servers to serve their customers. Amazon, they have much more than 100,000 servers. Facebook now have about 500 million servers to serve, more than 1 billion users. Because remember, whether Facebook or all these, users, they store quite a bit of information, whether it is images, videos, and so forth. And for those, you need a huge amount of servers and storage. And if we look into the future in terms of this area, so for example, by next year, the total market for cloud computing application in the UK is expected to grow to about 190 billion. Worldwide, 19, not 119, sorry. Worldwide is about 150 billion. And for example, Taiwan is creating a complete supply chain of cloud computing services and is expected to gain sales of around 10 billion US. The same thing in Japan. So basically, most countries and big companies are jumping into this wagon because it is here to stay. It's not something that, a lot of technologies, somehow they have a little bit of hype, then they disappear. Cloud computing is not hype. It still has some problems, as I will mention them later, but it is here to stay. And in fact, probably all of us somehow are using a cloud. In fact, Gmail is on the cloud. So now I will try to talk about some of the challenges from a computer science, computer engineer perspective that my research team is trying to tackle. It doesn't mean that these are the only research problems, but I believe these are quite important. One is in terms of the infrastructure itself and how to design or to deal with the networking challenges of connecting thousands and thousands of servers. Also, in terms of developing applications onto these data centers. The other is also you need to have appropriate protocols for communications within these data centers. So these are some of the problems that I will try to go through them, but not in detail. But I can give you all the information that you need in terms, if you want, for example, later on papers and so forth. I have all of them. But as I said before, there are many other important issues that I did not list here that I'm not working on them, but nevertheless they are important. For example, security and so forth. So one, in terms of the network itself, obviously, it is extremely important. And it underpins all the major data and center and and communication within the data center. Whether you are talking about the cloud computing application, whether you are trying to do server virtualization, for example, you are using VMware type of software, whether you are talking about security, desktop virtualization, input-output virtualization, everything depends on the network. And if we look nowadays at the trends of data traffic out there and applications and the infrastructures that we have, then we see that with the coming of the desktop virtualization, convergent fabric, now with the cloud computing application, there is a networking architecture gap. Meaning that the network nowadays, they are not able to support the major data that we see in big data centers and for cloud computing applications. So a typical data center nowadays, I mean, it is built around a tree structure. So you have here what they call top of the rack switches, and from these switches, then you will find servers and storage here. Then they will connect to what they call end of the rack switches, then into core switches. So this is typical infrastructure that we have nowadays. But the network bandwidth requirement is increasing as the node count increases. And basically, this network bandwidth requirement is doubling every year and a half. The other is that these core switches, they are becoming a bottleneck because basically all the data that comes here, then they have to go up the layers into these core switches. And also new application loads, they are placing much more stress on the network itself because most of these applications are what they call data-centric workloads. So basically, there is a real demand out there which is not being met by traditional networks. So that's why, in some sense, they try to use what I mentioned before, over-provisioning. But over-provisioning is a very, very costly solution. The other is, again, for the applications, let's say when you do a Google search. I mean, this Google search is basically based on an environment which is called MapReduce. So typically, this MapReduce is that you try, for example, if you are doing a search, you try to send your search in a distributed way over so many servers, and after that, you get your result into a single entry or multiple entries. So you have a map operation, then a reduce operation. And this map operation typically is very storage intensive. And the reduce operation, it is network intensive. So basically, in this case, for a data center itself, it needs to accommodate this type of typical applications that you find them in data centers where MapReduce is a major environment. There is also Hadoop, which is done by Yahoo, but this is a bit more popular or more used. This is created by Google. So if I look also, so that's in terms of networking requirement. Now, in terms of the cost, again, suppose you are trying to build 500,000 server data center, which is not unrealistic nowadays. I mean, there are data centers which go into the couple of 100,000 of servers. So if you are using, for example, gigabit Ethernets, and this is the cost of these gigabit Ethernets, and here I'm assuming a certain number of interface points. So in this case, for a data center like this, I need about 40,000 top of the rack 10 gigabit Ethernets. And this is in terms of end of the rack. So the costs can be in the billions. I mean, again, this is a very large number, but if you scale it down, let's say to even 100,000, then the prices still can be very, very high. And why, I mean, these prices are high is, again, because of the traditional architecture that these companies are using. So it is quite expensive, and it is not really scalable. And there are many other, things that we need to keep in mind is, again, in terms of the server count, in terms of the storage growth that I talked about, in terms of the internet traffic, in terms of the internet nodes, meaning that any of these parameters points to a high scalability rate in terms of these data centers. So again, here, in terms of the communication estimates, remember, for example, if I do Google search by sending, let's say, that one word that I'm trying to search, that in itself, it could generate tens of kilobytes of data. And that's the nature of these searches. So it does not mean that if you want to search for American University of Sharjah, meaning that you are sending just a few bytes. Yes, you are sending a few bytes, but within the network, it will generate thousands of bytes to get you the appropriate result. So basically, a clear conclusion here is that the communication efficiency and the network is extremely important. So there are many additional requirements. Again, I will not go through them, but each one of them is essentially also a huge research area. And again, probably I can see some of the students here. I'm giving you some pointers of some of the important problems that probably you want to work on in these areas. For example, in terms of fault tolerance and high availability. In terms of nowadays, energy saving within data centers is extremely important, because some of these data centers, the power requirement of a data center is sometimes as big as a small city. So it is not something that can be ignored. And efficiency and easy of management and so forth, and rapid provisioning, the deployment is also very important. So, I mean, I will not go in much detail about these, but for example, as I said, a traditional structure, typically they are based on these fat trees. However, these fat trees typically, they have poor fault tolerance, because if any of these links, especially on the top, breaks, then that can lead to a much lower efficiency, and sometimes you can isolate a certain part of the network. And also there is a bottleneck here. The nature of the tree itself has a bottleneck. I mean, people also, some companies, they are designing their data centers based on what they call the closed network. And the closed network has been around since the 50s. It was used for telephone communication. After that, it was used for internet switches and routers. And now it is being used in data centers. And it has a uniform high capacity between any two servers, which is quite nice. However, it can have a huge overhead if you want to make it totally non-blocking. And also, in terms of adding servers or constructing essentially a partial closed network, it is not trivial. Then, nowadays, companies and a lot of research is being done on using essentially a point-to-point type of networks. And like this one, which is designed by Microsoft, it uses a certain recursive nature. So basically, you start with a very small, what they call atom. And then you use this one to construct the next level. And the next level, you use this one to construct, to go to the next level. So it is done in a very recursive way. And this type of design essentially it can scale extremely fast. Meaning if you want to build exponential networks, it can be done extremely fast. And also it can have a very high bandwidth and fault tolerance and so forth. So one of the problems with this is in terms of wiring complexity. As you can imagine, it can be a nightmare because it contains too many wires and the wiring complexity within a data center, because a data center is essentially, again, it can be like a big room like this, or it can be as big as a football stadium. Then if you have too many wires, from maintenance perspective, it can be, it's not trivial. Then other research, they try to reduce this type of wiring complexity using this, what they call the BCube. It's the same, it has the same flavor, meaning it has a recursive flavor, but the problem is that its scale is much slower, meaning that to be able to build a very large network, the number of recursive levels can be extremely high. And if the number of recursive levels is extremely high, then in that case, in terms of routing can be very complicated. And most importantly, in terms of writing application on top of it, can be extremely complicated. Because at the end of the day, you want to write, to design and implement a cloud computing application on top of this infrastructure. So basically, nowadays, this type of area is extremely important. And it's a very hot area, this data center interconnect. A lot of companies are jumping into it, and they are trying to design a scalable data center interconnect. I mean, it's a similar trend to, let's say, 10 years ago about switches and routers for the internet. Now, that area is a bit mature. So this is the next challenge for companies like Juniper, Cisco, Huawei, and so forth. So in some sense, we also worked in this area as part of a big project that was sponsored by Huawei. And again, for some of you who don't know Huawei, it's a Chinese company, telecom company, but it is the second biggest telecom company in the world. In fact, it is much bigger than Cisco or Juniper. So basically, the analysis here for some of the networks that I showed before is we try to see their scalability, how they scale for a large number of servers. So the question here, what kind of scalability is good? And we did a bit of analysis. So I will, again, you can go to the details. I can give you links to the papers that we have on this. It's basically, here we designed what we call the HyperV Cube, and we designed another network which is called the flat net. So as you can see here, this in terms of the network layers. And as I mentioned before, the number of network layers, it can have a negative effect if it is large with respect to routing and also with respect to applications. So obviously something like this would be nicer, because here with just 2 to 3 layers, then essentially the number of servers that we can have extremely high. So basically the point is that how to design some kind of recursive network where the number of recursions is small. And that's basically one of the motivation that we have. So one of them is this HyperV Cube. This is its scalability order of magnitude. It is a recursively defined architecture. And basically, again, the key is not just the recursion itself, but how the various layers are connected to each other. And this needs to be carefully analyzed. So in our case, we used a pattern like this. And again, I will not tell you the motivation for this because it will take a long time, but it is done in the paper why we come up with such connections between the various layers. And the bottom line, essentially, the bottom line, how did we come up with these, is that we want to increase the scalability while reducing the number of layers. And of course, at the same time, you try to design a network where routing is simple. Because if routing is complicated, then it defeats the whole purpose. So basically, it will look something like this. Essentially, this is, for example, a certain atom at a certain layer. It could be layer 1, layer 2, and so forth. And you try to connect all these layers in this type of pattern, which is essentially this. And this is another visualization of the pattern. And again, when you have such a structure, then of course you have to design the proper routing algorithms for that. Because without routing, without simple routing, it defeats the whole purpose. So we have designed routing algorithms which are relatively simple, and they can be easily implemented in practice. Also, we have done a bit of evaluation because link availability, and as I mentioned, is extremely important. So we try to look at the connection failure versus the link failure. And as you can see, they linearly go with that, which is meaning it is close to the optimal. So, I mean, here, for example, as high as the link failure, let's say 20%, then basically the connection failure is around 40%. And the same thing here, for example, this is the link failure versus the average path length, meaning that because if you are designing 10,000 server and so forth, I mean, obviously there is a very high probability of having a certain failure. So you want to see the effect of that failure in terms of the connectivity between servers and in terms of the average path length. So here we did some analysis, and it compares quite nicely with other networks like the D-Cell, the BCube, which were designed by Microsoft. And here are some of the properties of this network. So I will not go through them in detail, but just to give you an idea. And as you can see here, even in terms of the number of links that we use for a HyperV Cube, it is much less than that for the networks that were proposed and designed by Microsoft. So in terms of the wiring complexity, it is much less. Then after we designed that network, and in fact, we got a patent out of that, we came up with another one, this one, which are in some sense similar in nature, but this one, I mean, the communication pattern between the various columns here is a bit different, with the goal of reducing the number of network layers. So here, the maximum number of network layers that we are advocating is 2. And with 2, basically, the network can scale even in the orders of 1 million servers. So basically, we try to minimize the number of layers, because when you design, you minimize the number of layers, then it becomes like a flat. When we say a flat network, meaning it's like a fully connected network. And the fully connected network has the advantage that we can, the design of application is very easy, because I don't care where the location of my servers are. Because if, for example, you have a network of diameter, let's say 50 or something, then the location of the servers are extremely important. And it becomes a nightmare from an application building point of view. So this is, again, even though it looks like the previous one, but it has a different communication patterns. And again, I will spare you from these. We also did the same analysis in terms of connection failure versus failure rate, and it compares favorably to other type of networks that are commercially available. And also here, we try to find the failure rate versus the average path length, meaning that if you have so many links that are failing, how it will affect the largest or the average communication path between two servers.